In this vector, we'll take a look at Cartesian vectors. And if you take a look at the graph on the right here, there are four vectors drawn, and they're all equivalent vectors. And they're really the same vector because if you take any vector and go from the tail to the head, you're going 1, 2, 3, 4 horizontally, and 1, 2, 3 vertically. Even this blue one, it's 4 horizontally, 3 vertically. And so the 4 and 3, you go horizontal first, the vertical change next. Those are called the components of the vector, the 4 and 3. And so that's the horizontal distance and vertical distance from the tail to the head of the vector. Now, of all these vectors are equivalent, are the same vector, the one that's drawn with its tail at the origin, right here, the blue one, is called a position vector. And the coordinates at the head of that vector are the same as the components of the vector. Notice the components are 4, 3. The square brackets means that's the components of a vector. If we write the coordinates of this point right here, that point right there is the point 4, 3. But the vector, if I call that the vector v, has components, square brackets, 4, 3. Now again, if the vector is drawn with its tail at the origin, the coordinates at the tip of the vector or head of the vector are the same as the components of the vector. Now adding Cartesian vectors, we're going to add these two vectors. And so in order to add them, we could draw a parallelogram or use the triangle law of addition. This is b plus a, or a plus b up here to give the white vector. So that's the vector sum by placing the two vectors head to tail. Now, if we take a look at the components, b is the vector 1, 2, 3, 4, 1, 2. So b is the vector 4, 2. A is the vector if we go from the tail to the head, 1, 2, 3, 1, 2, 3, 4, 5, 6. So that's the vector 3, 6. Notice that we add those two. Now, the vector that the vector sum, the white vector, the a plus b vector, if we go from the tail to the head of the vector, you're going horizontally 7 and vertically 8. So it would have components 7, 8. So notice we added the 4, 2 vector and the 3, 6 vector and got the 7, 8 vector. So notice that you can actually add the components 4 and 3 add to 7, the x components add to the x component, and the y components of 2 and 6 add to the y component of 8. So that's how you add Cartesian vectors. That's how you just add the like components. So the rule for adding or subtracting vectors in Cartesian or component form is a1, a2 plus the vector b1, b2 would be a1 plus b1, comma, a2 plus b2. So we add the two x components, we add the two y components. Scalar multiplication works in a very similar way. So c is the vector 4, 3. Now, if we were going to find the vector 2c, there's the vector 2c. Notice that 2c has components 8, 6. So notice all you actually do is you multiply all the components by 2. So 4 and 3 multiplied by 2 are 8 and 6. So the rule for scalar multiplication with Cartesian vectors is if k is a scalar and c1, c2 is the vector, then we just multiply the scalar in by all the components. So it would be k c1, comma, k c2. And that's true for all k contained in the set of real numbers. That's what the capital R stands for. A few examples. We're given these two vectors. We're asked to add m and p. So we're adding 4, -1 and 2, 5. So we go 4 plus 2 is 6, and -1 and 5 add to 4. So m plus p would be the vector 6, 4. 7p means we're multiplying p's components by 7. So 7 times 2 is 14. 7 times 5 is 35. To calculate 2m minus 3p, so this is 2 times vector m minus 3 times vector p, and so we would go and do the scalar multiplication first. So 2 times 4, -1 is 8, -2. 3 times 2, 5 is 6, 15. Now notice I'm leaving the subtraction sign here. I'm not actually expanding a -3 in here. You actually could do that, and then this would be plus -6, -15, and that would work. And so we subtract. So 8 minus 6 is 2. -2 take away 15 is -17. So that's the 2m minus 3p vector. Now, vectors in component form can also be used to prove certain properties of scalar multiplication and vector addition. And so we're going to prove this distributive property, m times a plus b is equal to ma plus mb. And so I would first have to define what my vector a and b are in terms of Cartesian or component form. So I'm going to call a the vector a1 comma a2 and b the vector b1 comma b2. So what I'm going to do is I'm going to evaluate the left side and the right side and show that they are equivalent. So m times a plus b, the brackets means that you add a and b first. So here's the same brackets here. So we're going to add vectors a and b. The m will get expanded in later on. So to add vector a1, a2, and b1, b2, we go a1 plus b1, and that's the x component, and we add a2 plus b2, and that's the y component. And then we multiply the scalar m in by both components. So m times a1 plus b1 would be ma1 plus mb1, comma, and the y component comes from multiplying m by the a2 b2 plus b2, which would be ma2 plus mb2. So we've simplified this. Now next we're going to evaluate ma plus mb and see if we get the same thing. So ma plus mb means we multiply a by m and b by m and then add them afterwards. So m times a1, a2 would be ma1, comma, ma2. m times b1, b2 would be mb1, comma, mb2, and then we add them. So ma1 gets added to mb1, and that's the x component of the vector, and then the y component ma2 gets added to mb2, and that's the y component of the vector. X component here, y component here. And notice that these two quantities are the same. And so because of the fact that the left side and right side worked out to be exactly the same thing, then we can conclude that m times a plus b is equal to ma plus mb. Now this is a proof for any vectors in two-dimensional space, because a1 and a2, b1 and b2 could be any real numbers whatsoever, and the scalar m could be any real number whatsoever. And so this is a proof for any vectors in 2 space. If you took specific numbers for a1 and a2 and b1 and b2, like let's say you made that the vector 1, 5, and this the vector negative 2, 6, and you let m be the number, let's say 9, then that would only be an example of this for one specific 2 vectors and a specific scalar. It would not be a proof for any possible vector like this is in 2-dimensional space. In example 2, we're given this 2 points r and t. At negative 2, 1 is where r is, and t is 3, 5. So there's negative 2, 1 and 3, 5. And so rt is the vector that goes from r to t. The tail is at r, the head is at t. So it says draw vector rt with its tail at the origin. And one way you can do that is to draw it accurately is use components. So to go from r to t, you go 1, 2, 3, 4, 5. So 5 is the x component, and then 1, 2, 3, 4 up, so 4 is the y component. And so we would just draw this vector over 5 and up 4 from the head to the tail, so the tail to the head. And so there's the vector rt with its tail at the origin. So what are the components of RT? Of course, they would be 5, 4, as I just read. Now, the next question is, how do the components of RT, the 5, 4, compare with the coordinates of the points at R and T, at the tail and the head? And this is actually getting at how do you find the components of a vector given where the points are at the tail and the head of the vector. That's what this is all about. And notice that if you take the coordinates at the head and the coordinates at the tail and subtract them, so where the head is of the vector minus the tail, so 3 take away negative 2 gives you the 5, and 5 take away 1, that calculation gives you the 4, the y component of 4. So you actually go the coordinates at the head of the vector minus the coordinates at the tail of the vector, and that gives you the components of the vector. And of course, so there's the components of the vector, the 5 and the 4. Now, how do we calculate the length or magnitude of the vector? Well, in this right triangle, the shorter sides in the triangle are 5 and 4. So we can use Pythagoras' theorem. The length of this side squared would equal 5 squared plus 4 squared. Now, since you're always finding the length of the hypotenuse, then we'll take the square root of both sides. So the magnitude of the vector is just the root of the x component squared plus the y component squared. So the root of 5 squared plus 4 squared. And 5 squared is 25, 4 squared is 16. 16 and 25 add to 41. So the length of the vector, this magnitude, is the root of 41. Now in E it says find two unit vectors parallel to RT. Unit vectors are vectors that have a length of exactly 1 unit. This is much longer than 1 unit. The square root of 41 is between 6 and 7. The square root of 36 is 6. The square root of 49 is square root of 49 is 7. So this is a little bit over 6. Now, the way you find unit vectors is you take the vector and you multiply it by 1 over its length. So 1 over its length, it's really kind of like dividing it by how long it is to make it 1. Like if you take the number 10 and divide it by 10, you get 1. If you divide a number by itself, you get 1. So that's the idea here, although dividing a vector by a number isn't really defined. So instead of dividing it by the length of it, we multiply by 1 over the length of it. That's the more formal way to do that. So the length of RT is the root of 41 we just found here. And here's the vector RT's components. So we multiply 1 over root 41 by 5, 4. And so 5 times 1 over root 41 would be 5 over root 41. And 4 times 1 over root 41 would be 4 over root 41. These each have a denominator of 1. So in the denominator, 1 times root 41 is still just root 41 in the denominator. Now it says find two vectors. Another vector that would be still parallel to RT would be the opposite of this vector. So that's another possibility that we could list. I'm not saying that these are equivalent. There's no equal sign here, but the opposite of this vector would still be exactly 1 unit long, just in the opposite direction, still parallel to RT. So in general, the components of the vector from the point x1, y1 to the point x2, y2 is, and I'm going to draw a little bit in my diagram. So there's the tail of the vector, there's the head of the vector up here. And I'll draw a little bit in to make a right triangle here. Now, if this is the point x1, y1 and x2, y2 up here, this point here has the same x component, x coordinate, as that point, and it's the same height vertically as this point. So if y1's the y component there, then y1's the y component there. So that's why we would call that point the point x2, y1. The distance horizontally across here is the difference between this x component, or coordinate, and this x coordinate. So we will go x2 minus x1. And the distance here is the difference between the two y coordinates, so the y2 minus y1, because that's the vertical change in height. So the x component of this vector would be x2 minus x1, because that's the horizontal distance. And the y component would be y2 minus y1, because that's the vertical change to go from this point up to this point. And so there's the general rule. It's the same thing I was illustrating in the example on the previous page, but in a more formal form. In general, the magnitude of the vector x2 minus x1, y2 minus y1 is the root of the x component squared plus the y component squared. And again, that's really just Pythagoras' theorem. Now, we don't normally write components in terms of two different numbers subtracted, so we would normally call it like the vector pq, and so it's just the root of p squared plus q squared. The x component squared plus the y component squared, take the square root. In example number 3, two monster trucks are pulling a shed. The first truck pulls with a force of 4,000 newtons east, and the second with a 5,000 newton force at a bearing of 20 degrees. So remember, true north is 0, bearing of 20 degrees is at 20 degrees toward the east. Find the resultant force applied to the truck. So first of all, we have this truck pulling straight east with a force of 4,000 newtons. And then here's the second one at an angle of 20 degrees with north, pulling at with a force of 5,000 newtons. Now what we're going to do is we're going to write both of these vectors in component form and then add them together. So this is actually the resulting force. It's going to be somewhere between the two of these. Now, In order to get the components of T1, and forget about the 70 for a moment, I clicked one times too many. This vector right here, and that's not labeling this force vector, this is just referring to the T1 vector here. The horizontal component of that would be, since it goes straight to the right along the x-axis, the horizontal component would have to be 4,000, and it doesn't go vertical at all, so that's why the y component is 0. Now, in order to find the components for this vector, if that's 20 degrees, then it would make a 70-degree angle with the positive x-axis. And this refers to an earlier lesson in this course, finding the horizontal and vertical components for a vector. And so what you do is, because that's 70 degrees, the horizontal component along the bottom here, and it looks like this, we're actually making a right triangle. So we go straight down here. So the horizontal component is this component here, and that's the adjacent side for that 70-degree angle. And so the adjacent side and the hypotenuse are used to find out how long that is, so that's why it's cosine. So you go the size of the hypotenuse times the cos of the angle. This vertical side here is the opposite of that 70-degree angle, opposite over here. And so that vertical side is the length of the 5,000 times the sine of 70 degrees. So 5,000 sine 70 gives you the vertical component. And so we would calculate those in a scientific calculator, 5,000 times the cos of 70 and 5,000 times the sine of 70. So those are the components of this vector. Horizontal component is the 1710, vertical component is the 4698.5. And then we add the two of them together to get the net force, the F. So F is T1 plus T2. And so we actually would just write the 4,000 comma 0 plus the T2 vector and just add the two together. So 4,000 plus 1710.1 would be 5710.1, and 0 plus the 4698.5 would be 4698.5. So those are the components of that vector. Now, if we want to know how big the vector is, really want to know, first of all, what its magnitude would be. And so we just use the magnitude of a vector formula from the previous page, and it would be the root of the x component squared plus the y component squared. And so if we square those, add them together, we get a very big number. Let's see now, 54,681,144.26. And then we take the square root of that. So the magnitude of F is about 7,395 newtons to the nearest whole number. Now we need a direction. We need to know how big this angle is here. So this means for this vector, those components, that this component here, that's the 5710.1, and this vertical component here, did a much better job in that one, is 4698.5. So we really just have a right angle triangle here, and it's in order to find the angle here, that's the opposite side, that's the adjacent side, so we can use tan to find this angle right here. We'll call it theta. So the tan of the angle would be 4698.5, over the 5710.1, which is about 0.8228, and then we take the inverse tan of that, and so this angle is about 39 degrees. So we could make our concluding statement: the resultant force applied to the shed is 5,395 newtons at an angle of 39 degrees to the 4,000 Newton force. Or that's 39. We could instead state this angle right here, which would be 51 degrees. So we could say it's a bearing of 51 degrees instead. Now a little bit about standard basis vectors on this page. And these are the standard basis vectors. They're 1 unit long in the direction of the positive x and y axis. I is the name for the standard basis vectors in terms of the in the direction of the positive x axis, and j is the one in the direction of the positive y axis. And they're each exactly 1 unit long. The reason they're called the standard basis vectors is because any other vector can be written in terms of them very conveniently. So I would have components, that's the vector 1, 0, and j is the vector 0, 1. And again, they're unit vectors because they are exactly 1 unit long. So any other vector in the plane can be written as a very simple linear combination of these two vectors. So for example, if I drew this vector here, then in order to write that as a multiple of I plus or minus a multiple of j, then it would be 4I plus 2j. So notice that that vector is the vector 4, 2, and 4 is the multiple of I, and 2 is the multiple of j that would add to the 4, 2 vector. So that's how you write any vector this is called standard basis form. 4, 2 in component or Cartesian form is 4i plus 2j in standard basis form. So in general, the vector mn can be written as mi plus nj.